The universe is three-dimensional. Okay. No, the universe is four-dimensional. 3 dimensions for space and 1 for time. Okay, duh, what are you talking about? The universe has 9 dimensions. Okay. Come on, guys. The universe is flat. Wait, what? However strange it may sound, all these statements are kinda true. How come? The theory of general relativity allows for the universe to take one of 3 forms. It can be flat, like a sheet of paper. It can be completely closed, like a sphere. Or it can be shaped like a horse's saddle. It's very important to figure out the shape of the universe. This way, we can learn about its past and future. It can answer crucial questions. Is the universe going to expand forever, or will it eventually collapse? Is it finite or infinite? Here, we need to consider 2 factors: the density of the universe and the rate of its expansion. Now, hear me out. About 68% of the universe is dark energy, 27% is dark matter, and the remainder is normal matter. That's what stars, planets, and our bodies are made of. And when we speak about the universe's density, we mean the amount of matter packed into a given volume of space. And the density of the universe is so great that its gravity is more powerful than the force of its expansion. Then the universe will curl into a sphere. This is what we call the closed model. The coolest thing about such a universe, even though it is finite, it has no bounds. However paradoxical it may sound, if you found yourself in this universe, you would travel its space forever without falling over an edge or hitting a wall. But if the density of the universe was low, it would be unable to stop its expansion. In this case, space will warp in the opposite direction, creating an open universe shaped like a saddle. But the most popular theory, and the most bizarre-sounding one, is that the universe is flat. It might be possible if its density is just right, and it expands in every direction without curving negatively or positively. Scientists claim that it's the most plausible scenario, by the way. So, if you're disappointed by our planet's roundness, the flat universe might come as some consolation. But what does a flat universe mean? I mean, our 3D world seems very real. Can it be just an illusion? Nah. The flatness of the universe isn't that two-dimensional flatness you might be imagining right now. To help you understand this concept better, I'll tell you this. In a flat universe, 2 rockets flying next to each other will always remain parallel. In a closed universe, their paths will diverge, and they will follow the curvature of space and eventually make a loop and meet where they started. And in an open universe, these rockets will separate and never come across each other again. Of course, it'll take a lot of time to prove that the universe is indeed flat. But so far, astronomers don't have even the slightest reason to doubt this theory. All the data they have is consistent with this flatness. For example, the imprints left on galaxies from sound waves that occurred right after the Big Bang also support this theory. In other words, right now, scientists agree that the universe we live in is like a 3-dimensional sheet of paper. Good luck trying to imagine this. But if this idea is wrong and the universe is actually curved, it must be ginormous, because those 93 billion light-years we can observe aren't a large enough portion to let us see even a tiny curvature. So, it might be wrong to say the universe is flat. It's probably better to announce that the little bit of the universe we see is flat.
You wake up and can't recognize your room. That's definitely it, but your desk is on the wall, and the dresser is on the ceiling. It's closed, but you can somehow see every folded t-shirt in it. You wipe your eyes. Nothing changes. This isn't a dream. Welcome to the 4th-dimensional world. Wait, rewind. To understand the 4th-dimensional world, we need to look at the others. So, a 0-dimension world is just a point. Now, if you expand it, you get a 1-dimensional world that's a simple line. It only has one measure, and that's length. The creatures living in this world can only move in one direction, either left or right. In general, a dimension is a direction in which an object can move. So now we'll add another line perpendicular to the one we have. We get a flat surface with a length and width, like a piece of paper. The flat creatures that live in a 2D world can move left and right, and now forward and backward. To turn this flat paper world into one we're more familiar with, we draw parallel lines from each corner of the square. Now we get height, the third dimension. The objects of this world have three measures: length, width, and height. They can move in three dimensions: left and right, back and forth, up and down. That's the world we live in. But now we need to figure out where to put the next perpendicular line to get a fourth dimension. It's no easy task, because this fourth dimension, as well as the fifth and 12th ones scientific theories say could exist, are hidden from us because of the limitations of our perception. While we were going through the first three dimensions, we could see that with every next dimension, we expand the possibilities. The objects become more complicated. As inhabitants of a 3D space, we can easily imagine what 1D and 2D worlds are like because they're part of our own. But for residents of those worlds, it's not that easy to understand ours because they're just not able to perceive it. Why? Imagine you're one of these 2D flatlanders and you're living your simple flat life. If a sphere, a 3D object, somehow appears in your world, the only thing you'll be able to see is a dot that appears out of nowhere, and then grows into a longer and longer line, and then shrinks back down into a dot before disappearing. A flatlander could combine all these lines to get a circle, or if he could look at it from above, he can't, that would involve height, it would just be a dot growing into a larger and larger circle and then getting smaller. Either way, our flatlander ends up looking at a flat circle, not a sphere. That's exactly what will happen to us if we try to understand a 4D object. We'll see it like a 3D object, appearing, somehow changing, and then disappearing. We wouldn't be able to make sense out of it. For example, let's take a 4D hypersphere and put it in our world. Here's what you'll see. Looks like a regular old sphere appearing, growing, shrinking, and disappearing. Good luck trying to combine the spheres all together to make sense out of its 4D shape. Okay, let's try it with something a little easier. Remember, 1D is a line, 2D is then a square, and 3D adds more perpendicular lines to get a cube. To get a 4D cube, called a tesseract, we connect two cubes. We know that every side of a 3D cube is a square. In a tesseract, every side of it is a cube. This shape looks really confusing, especially if we realize that it's a 3D projection of a 4D object on your 2D screen. Just like the Flatlanders, we're unable to fully understand what a higher dimensional world is like. Even scientists have a vague and limited perception about it. They mostly describe it in complex mathematical equations, not physical objects. But think about it this way. Technically, every single day, 4D or even 10D beings could enter our world, and we wouldn't even know it. Now, if the first, second, and third dimensions are length, left and right, breadth, back and forth, and height, up and down, what does that make the fourth dimension? How about a real-world example? There are 2D ultrasounds that show a flat black and white image, mostly made up of outlines. Then there's 3D. It's basically like a normal photograph you'd see in an album. Things have a form, depth, shadows. Then there's 4D ultrasound. This is an image that's constantly being updated with time. The fourth dimension. Some call it strength, but it's basically space-time, in and out and always. So you wake up in your room in a 4D world. The planet is a hypersphere. Everything around you is as if you lived in a sphere. Your wardrobe is still up on the ceiling, and you need to get dressed. Wait, where are you going? Stay right there. I know you still think the shortest way from A to B is a straight line, but you're in a 4D world now. The shortest way here is through. So just look through your wardrobe, find your favorite t-shirt and jeans, and grab them. That's better. Hey, your roommate is making coffee. Let's grab something to eat too. You could just teleport there, but let's take the long way. No, not the stairs, through the walls and floor. Doors and stairs will probably be non-existent in a 4D world. There's your roommate. Don't be confused, he's okay. Albert Einstein called the 4D universe a space-time world. Here, the past, present, and future all come together. So, like every other object, your friend exists in every moment of his entire life. I know what you're wondering. If you can move through walls, can you move through people too? Yeah, but please don't reach into his head and tickle his brain. That's taboo in this world. Even if it can be done, it shouldn't. Here's another cool thing. You can see people's emotions. See the yellowish shadow around him? It means he isn't in a very good mood. But wait, mentally, you don't need words here. They're too slow. You can reach any person mentally within a moment, even if they're on the other side of the planet. Now, let's grab your sandwich, laptop, some work papers. Oh no, you don't need this bag. Forget it. You have pockets, right? Put it all there. You'll see it fits perfectly. There's endless space. Well, and no reason to take things with you when you can instantly teleport. Forgot your wallet? 1 second. Now you have it. Okay, you're a little late already. Work starts at 9 and your boss is going to be seething. But don't worry. Remember, you exist in any time, present, past, and future. Even though it's 9:12 already, just get there by 9. In fact, let's take a vacation day. Teleport to Rome. See all the sights as they were through all of time and history. Master the Italian language. Where to next? When to next? The choice is yours. You can always travel back and get to your job like a punctual hard worker. And still, life in a 4D world would probably be something entirely different than even my wild imagination can come up with. So, I'll let you finish this story down below. The Milky Way is one of the biggest mysteries out there, literally. It's hard to figure out how big our home galaxy is, and one of the main reasons is because we live in it. Think of it as walking around a mall. You can tell it's big, but you can't be certain until you actually see it from a bird's eye view. The Milky Way consists of billions of distant stars that look like a string of lights from afar. So you just need to measure the distance between these stars and voila, you have the answer. Not really. I might have forgotten to mention opaque clouds of dust blocking your view. Some scientists were stubborn enough to run computer models of how galaxies form and evolve. There's a halo around our galaxy, so the scientists wanted to see if there was some sort of a dead end in the Milky Way. They found out that the Milky Way spreads for 100,000 light-years away from its center. It likely means that the entire galaxy is around 200,000 light-years across. The problem with this estimation is that halos don't tend to have some final border since they simply fade away. It's like pointing a flashlight and trying to see precisely where the light ends. In 2013, the Hubble Space Telescope captured an image of something 25 million light-years away. It turned out to be a spiral galaxy, later called ESO 3738, with at least 7 other galactic neighbors. And this galaxy is as thin as a pancake, a very shiny pancake. The telescope also took a photo of another galaxy cluster 65 million light-years away. It was called IC 335. It's another glorious glittering pancake floating in the vastness of space. The images the telescope took aren't the most accurate. It's hard to tell what exactly you're looking at. These disk galaxies have lots of dust clouds that can stretch for hundreds of light-years across. They're mainly located near the centers of galaxies and are invisible in regular light, but they can be detected with the help of a blue filter. Anyway, this IC 335 galaxy is an oval disk with huge clouds of gas and dust. This means stars constantly appear there. But not all galaxies create stars. A galaxy is born as a giant ball of slowly rotating gas that is steadily collapsing in on itself. As it starts spinning faster and faster, the pancake shape is formed. Ooh, pass me the syrup. It's like spinning pizza dough in the air after rolling it into a ball. The topping is stars, and the sauce is clouds of dust and gas. Are you getting hungry like me? Some galaxies can lose their gas and dust if they become part of a galaxy cluster. Then all these mini-galaxies orbit their common center of mass, with gas separating them. When a disk galaxy dashes through them like a speeding train, the pressure can blow away this dust and gas. From far away, it looks like you're staring at a DVD you're about to play. But if you traveled millions of light years to get a closer look, you'd see a dim disk filled with stars. You wouldn't even be able to tell you're inside it. You'd also see a bright blob of dust left by the red giants in the middle of the galaxy. Red giants are massive and very bright stars with low surface temperatures. But the images of these galaxies don't actually show us their real color. Cameras make up some of these hues so that you don't have to look at something fuzzy or grainy. People don't actually know the real colors of distant galaxies. Our galaxy has a lot of gas inside, like me, so we don't need to expect our home to dry up anytime soon. In fact, the Milky Way still produces new stars, around 7 a year. But some galaxies fade out when they can no longer create stars. In the industry, they call it strangulation, and it happens when galaxies run out of gas, which means there's no more new material that can be used for star making. Gas and dust aren't the only things you can find in a galaxy. Just like a magician pulling a rabbit, flowers, or other things out of their magic hat, galaxies have other surprises, like planets, those balls of matter spinning around themselves and around other things. Well, technically, planets are far from being perfectly round in shape, but they aren't also flat like spiral galaxies. It's mostly because of gravity. Its force is so strong that a planet pulls everything towards its center, taking the shape of a sphere. In the process, all the edges and anything else that might stick out gets smoothed out. But the smaller a spacebody is, the less round it is. Take a comet. It doesn't always have a smooth surface. It's small, and therefore, its edges are rugged and pointy. Given the size of Earth, it's safe to say the gravity is strong here compared to that of the Moon or any smaller-sized space object. And because of our planet's constant rotation, there's an outward bulge on Earth. This tug-of-war between the gravity pulling inward and the planet's spin doesn't allow Earth to be a perfect ball. On top of Earth not being a perfect sphere, the planet is also tilted. This design flaw is responsible for the seasons we have. This tilt could happen because millions of years after Earth was formed, it probably collided with a protoplanet, a large space body developing into a planet. Venus is unique because it rotates backward compared to the rest of its peers. If you were standing on Venus, the hottest planet in our solar system, you'd see the sun rise in the west and set in the east. But you'd have to make it on time to observe this phenomenon. A day on Venus lasts for more than 240 Earth days. For a long time, scientists believed that the sun's strong pull on Venus was responsible for such a long day. But new theory claims that Venus used to spin just like Earth and the rest of the planets. But at one point, it just flipped its axis 180 degrees. It doesn't mean the planet abruptly stopped halfway through the rotation and started to move backward. When theory suggests that a large comet or object struck the planet in the past. This might have caused it to change the direction of its rotation, but many scientists doubt this theory. If you observe the moon for some time, you may notice that it's the same face staring at you every night. The truth is that the moon does rotate, but very slowly. It takes our planet's natural satellite 27 Earth days to rotate around its axis. Plus, the moon rotates at the same rate that it orbits Earth. The side we always see is called the near side of the moon, and the side that's not facing us is, you guessed it, the far side of the moon. It also has the nickname the dark side of the moon. Uranus's rotation axis is 98 degrees relative to the plane of the solar system, which basically means that the planet spins on its side. For a while, scientists believed that a large object firing through space knocked into Uranus, causing it to tilt. But here's one problem. Uranus's moons are covered in ice. A collision so powerful that it made the planet tilt would have resulted in disrupting the moon's movement and their position. But they seem relatively untouched, and all the ice covering them is still intact. But any major changes happening with Uranus would have generated enough energy to melt the ice. Another reason for Uranus's strange position might be its rings. Yup, Uranus has rings just like Saturn, except they're lighter and fainter. Saturn's rings are mostly billions of chunks of ice and rock floating in orbit. Some particles can be the size of a pebble, while others can reach the size of a house. Wow. Other particles are broken up comets, asteroids, and moons torn apart by Saturn's gravity. If you observe the rings from afar, they look like colorful stripes made up of thousands of different streaks, but there are actually only 8 layers of rings. Uranus might have had rings that were just as glorious as Saturn's around 4.5 billion years ago. The balance between Saturn's gravity and its rings might be responsible for keeping the planet upright so that it doesn't tilt over. If Uranus had the same rings, they could prevent the planet from toppling over. The way to solve Uranus's tilting problem might be for the planet to get its rings back. They would help Uranus keep its balance. On the other hand, hey, we like it just the way it is.